So this video lesson is all about what we call prime factorizations of integers. Now it'll go over what a prime factorization is, how to find a prime factorization, certain important properties of prime factorizations, and then give you a chance to actually find and write out prime factorizations for certain integers. It's also important to remember that, like most things in number theory, when we're talking about prime factorizations of integers, we're probably referring only to positive integers. And so that's what we're going to be looking at today, is how to find the prime factorization of positive whole counting numbers. Now, this idea of prime factorizations is actually so important in the field of number theory that we have something called the fundamental theorem of arithmetic that we're going to see a version of as a part of this video that underlies almost everything that we're going to do, not just in this chapter, but pretty much everything in number theory is based on the idea of the prime factorization and the fundamental theorem of arithmetic. This is the core of the whole field of number theory, is this idea right here. So before we get into prime factorizations, though, we need to take a quick review of factors and what they are. So a factor of a number is one that divides evenly into that number, and by evenly we mean with no remainder. If this isn't in your notebook already, go ahead and pause the video and write this definition down so that we can talk about it a little bit more and then move on to prime factorizations. So in terms of factors being numbers that divide evenly into that number, if we start with a number like 20, there are lots of different ways we can make 20 using a product of two numbers. Like, for example, 2 and 10. 2 times 10 is 20. 20 divided by 2 is 10, no remainder, so 2 is a factor of 20. 20 divided by 10 is 2, no remainder, so 10 is a factor of 20. We can do the same thing with 4 and 5, and we can also importantly do the same thing with 1, because 20 divided by 1 is 20, again, no remainder, and 20. 20 divided by 20 is 1. Again, no remainder. So these are the things that we call factors of a number. And factoring is where prime factorization starts. So if we have a grove of, let's say, 12 maple trees, and we're trying to look at the factors of those numbers, which might help us put it into rectangular rows, well, we know we can break 12 into 3 times 4. That is one way that we can use a product to create 12. Now, 3 and 4 are two different types of numbers. 3 is a prime number. And prime numbers are pretty foundational in number theory also. 4 isn't, which means that we could actually take that composite factor 4 and we can break it down even further into 2 times 2. And since 2 is a prime number, the smallest prime number that we have, we can't really break down any of the other factors of 12 that we see any further. So we're left with 3 and 2 and 2. And starting with a composite number and choosing a way to split it into a product, and then taking any composite factors that we found and continue to split them in the product of two numbers, gives us something that we call a factor tree. Here it is a little bit neater. And a factor tree is something that's going to help us break down a composite number into not just its factors, but into its prime factors. So go ahead, pause the video, write down this definition as well as this factor tree for 12, come back when you're ready to talk a little bit more about it, and move on. So it's important to recognize that we just didn't pull every factor of 12 that we could find. We started with one particular one. And then when we got to a prime number, that is the end of a branch, part of why we call it a tree, and we can circle it. I prefer to circle it so that we know that that branch is actually ended. And then we take any composite factors we have remaining and we break them down. In this case, 4 into 2 and 2. And it's an important property of a factor tree that if we've done our division and multiplication right, if we haven't accidentally strayed into the world of addition, because everything in number theory is based on multiplication and division, then the ends of those branches, all of those prime factors, should multiply together to get us 12. And in fact, 2 times 2 times 3 is 12. And if we were to write those prime factors multiplied by each other, so that 2 times 2 times 3 is equal to 12, this here, that string of prime numbers that multiplies together to make a other particular number, that is called the prime factorization. So go ahead, pause the video, write down not only the definition of prime factorization, but also the prime factorization for 12, and then come back when you're ready to move on. And this here is a very, very important concept in all of number theory. The idea that a number, a composite number, can always be written down as a string of prime numbers multiplied together is exceptionally important. And basically what we're doing with a factor tree is we are taking a large complex composite number. 12 is not that big, but it's still a composite number. And we're breaking it down into smaller individual pieces, like you would if you had a large Lego structure, even a small Lego structure, and you wanted to break it down into its smallest component pieces that could not be broken down any further. You see where this analogy is going here. The pieces that can't be broken down any further are like prime numbers, and the big structure that we're going to break down is a lot like our composite numbers. We can choose to break it into a single prime number and a perhaps other composite numbers, just like if we're taking apart a Lego structure and we really want to break it down into those individual Lego pieces. We just have to continue to break it down until we get to these indivisible little things. The indivisible little Lego blocks are like the primes. And an important piece of that Lego analogy is that no matter how you start breaking apart that Lego structure, the underlying number, if you start with the same structure that you did before, the underlying indivisible blocks that you used will not change, no matter how you choose to break the structure apart. And that's a lot like prime factorizations, because we have several different ways we could potentially start breaking down a number like 24. We could start with 6 and 4, which break down further into 2, 3, 2, and 2, or we could start with something like 3 and 8, and 8 breaks down into 2 and 4 breaks down into 2 and 2. Again, if we end up with a composite here, we just continue to break down at the end. But something that you should notice is that no matter how we started there, the primes that we ended up with at the end were still 3 2s, and a 3. And that's the other important part of a prime factorization. No matter how you start breaking a number down using its factor tree, the underlying factorization will always be the same. Just like breaking apart a Lego structure will always give you the exact same individual Lego pieces that you used, no matter how you start or how you continue to break it down, if you really do truly break it down into small indivisible pieces. And because we're based on multiplication, these numbers, 2 times 2 times 2 times 3, there's only one product for them. The only thing that they can multiply together to get is 24. And so no other number can have the exact same prime factorization of 24. And that's something that we call in math uniqueness. And this is a variation of the fundamental theorem of arithmetic that is extremely important to us. And that's that each number has a unique prime factorization. Not just that it has a prime factorization, it has a unique one. That is, each number has exactly one, no matter how you factor it. There are not multiple for each number, and it is the only number with that particular factorization. Go ahead, pause the video, write that down, and come back when you're ready to go on to some practice problems. So the last thing that we're going to say about prime factorizations before we move on to some practice problems is that you'll notice in 24 two things. One, that the primes are written from least to greatest. And that's not something that we have to do. Multiplication is commutative, but it's something that's going to be really helpful, and it's convention to write the primes from least to greatest. That means we all sort of agree that that's the way that we're going to do it, and then everybody follows that agreement. The other thing is that we want to take strings of primes that are identical and condense them into exponents whenever we can. So 2 times 2 times 2 is actually 2 to the third. Mathematicians very frequently use things like exponents to make long strings of multiplication a whole lot shorter. So we use exponents when we can, and we write our primes from least to greatest. So go ahead, pause the video, create the factor tree for these 3 numbers right here, write out the prime factorizations using exponents if necessary, and with their primes from least to greatest, and then come back when you're ready to see the answers and wrap up the video. So for 42, we can break it down into 7 and 6, and then 6 into 2 and 3. And so 7, 2, and 3 are prime. Therefore, the prime factorization of 42 is 2 times 3 times 7. That will give you 42. It is the only number that has that prime factorization. That is the only prime factorization that you can have for 42. For 18, we can start with 2 times 9. and 9 is 3 times 3. So the prime factorization for 18 could start as 2 times 3 times 3, but we want to condense those 3's into 2 times 3 squared. Again, that is the only prime factorization for 18, no matter how you split it in the factor tree, and that is 18 is the only number that has that unique prime factorization. And then finally for 135, that's 5 times 27. 27 is 3 times 9, and 9 is 3 times 3. So the prime factorization for 135 is 3 cubed times 5. Again, this is the only prime factorization we would get for 135, no matter how we split it, and is the only number that has that unique prime factorization. So as a quick review, we can use a factor tree to break down a number into its most basic prime factors, like we break apart a Lego structure into most basic indivisible little pieces. And when we write out those prime numbers that we've gotten from a factor tree from least to greatest, including exponents, and say that that product is going to be equal to our number, we create what we call a prime factorization. Prime factorizations are unique. There's only one for each number, no matter how you initially factor it, and it is the only number that has that particular prime factorization.